chip architectures becoming much more complex with chiplets. The migration from monolithic SoCs to chiplet-based design is increasing a confusing array of options and trade-offs for design teams working at the leading edge, and the number of choices is only gonna increase as third-party chiplets begin pouring into the market. That hasn't damped the appetite for chiplets, however, which are deemed essential for future generations of semiconductors for several reasons. Among them, AI, whether it's in a data center, a car, or even a mobile phone, demands an orders of magnitude improvement in performance, using less power to process large volumes of data faster. The area of a chip used for additional feature is increasing. The wires and SRAM are no longer scaling fast enough to fit them onto a single chip, so they are being disaggregated into smaller chipsets and assembled in advanced packages. Breaking complex into the smaller pieces allowed for much more customizations, particularly for domain-specific applications, and potentially lower cost and a faster time to market at some point in the future, especially if a plug-and-play chiplet marketplace becomes viable. So we predicted that this year about 50% of high-performance compute will be multi-die. That Mick Posner, as Vice President of Product Management for High-Performance Computing IP Solutions at Synopsys. That's probably conservative, and 100% of the AI designs are multi-die because of their requirement of the high bandwidth and scaling, and they have to be designed like that. The trend we are seeing, which is gonna change everything yet again, is 3D, and this means the logic to logic stacking. What we see happening in 2025 is that more customers are moving to prototype stage where they are preparing to do a 3D design. They are not in a production yet because they need to prove things like hybrid bonding and through silicon vias between dies. Face-to-face bonding has an impact on their designs, and it has a lot of impact on IP. The figure 1 is a multi-die chiplet design through Synopsys. The increasing amount of IP is being hardened into chiplet. Large systems companies, which account for roughly 45% of leading-edge design today, have in limited experience developed that IP, and processor giants like Intel and AMD, which previously developed all IP internally, are looking to cut costs and speed time to market by leveraging third-party chiplets. That has engendered an entire new ecosystem. This one focused on a custom and semi-custom chiplet, as well as various assembly and package options, novel PHY, and new material and strategies for dissipating the heat. Has observed a number of the changes as monolithic design evolved into chiplet. In monolithic design, it used to be that signal integrity was done by the separate group people on the PCB side, and they perfected the art, said Subramanian Lalagudi, product specialist at Siemens EDA. So that there are a process as to how they wanted to sign off on compliance today for chiplet. There are different protocols: USB, PCIe, MIPI, SATA, and the process is clear. If you are a chip designer, designing transceiver, if you are a board person like HP or somebody else designing the board, or if you are a repeater company trying to take that amplifier, send it to something, the process is clear, and the standard evolved to the compliance required at the transmitter. But what is the compliance required at repeater? What is the compliance required at receiver, both for a serial standard and for parallel standard? Serial is point-to-point. The parallel is basically the DDL application there. The energy per bit was all pretty high, so in the PCB, so they could tolerate it. It's a bigger surface area. When the chip were monolithic, there was just appropriate consideration. There was no standardization, Largudi said. The moment chiplets came out, they needed to do static timing analysis, which is a clock-to-clock task, which makes sure all the bits arrive on time before it could latch on and go and do that. There is a setup time, there is a hold time that they have. This used to be called static time analysis, but the moment they introduced the chiplet, which means the chiplet guys and producers may be different from guys who integrated them together. Intel and AMD have already shown that Intel has taken FPGA designs they can mix and match stuff. They can go ahead with the processors on the technology node. They can go with the chiplet on older technology nodes. This is beneficial because now they can focus on what they are really good at. The partitioning is paramount. The first thing the design team needs to understand is how to partition the chiplet system. Letizia Giuliano, Vice President of IP Product Marketing and Management at AlphaWave Semi, explained the first things to naturally scalability are IOs. Those types of the building blocks don't scale with the process node. It's easier to keep those in older process node and to keep your computer power in advanced technology node. The first things we do with our customers is help them disaggregate the system. So we talk about I/O disaggregation and memory disaggregation, and we talk about the compute, where they can take advantage of the latest technology and the latest power and performance benefits using a leading-edge technology node. Where the companies are today on the chiplet adoption curve at varies clearly, we are seeing two categories of customers, said John Lupinski, Vice President of Product Engineering at Blue Cheetah. One is still learning about the chiplets and trying to figure out it, and they know their product eventually will have to be chiplet-based. They are trying to understand the interconnected packaging technology, what they can do, and the benefits they can achieve. The second category is trying to tape out real solutions to get a production demo at conferences. They know they have so many hundreds of terabits per second, and they are trying to move that from chiplet to chiplet. This is where much of the high visibility chiplet work currently is focused, particularly for data centers, industry, and automotive applications, where the UCIe and a bunch of wires provide a standard way to connect devices. That's just an important piece of a much bigger puzzle. Getting data to and from chiplets using those standardized protocols and routing it to whenever it needs go opens the door to sort of the possibilities, starting with moving data through a physical layer file. In the past, files were largely proprietary because most chiplets were developed in-house. Exception is HBM, but as more third-party chiplets are included in design, there is growing focus on how to improve the data speed and ensure the integrity of data at every level possible. If you use one vendor's file on both sides, it's pretty guaranteed to work, said Ramin Parjadra, CEO of Alien. And an important reason this interoperability has been slow to come to market is that the big companies put fear into the minds of their customers, and unless you use the same technology on both sides, you can guarantee that it works smoothly or flawlessly. These files are not different from the sellers today. In fact, they are simpler than the sellers because a channel is simple. There's no difference, and it can easily be adapted and built to be interoperable. Others agree. What customers are looking for is the maximum bandwidth at a lowest power profile, said Bluchita Lupinski. There are only two ways to do that. One is the legacy architectures like SATAs. Some of the UCIe vendors are jumping the clock right up. The problem is your picojoules per bit is gonna way up too. And if you try to take one of those macros and do 100 terabits per second, your power consumption is easy. That's a big area of focus today. How fast data moves from a chiplet to chiplet or chiplet to memory has a big impact on overall performance of the device, and there are multiple ways to approach it. Typically, clock schemes are synchronized so that the computation from the multi-threaded applications can be parsed and then combined. Any delays at a point that any delay at any point can increase latency, which reduces time to result. Or put simply, a system is only as fast as the slowest component in that chain. But clocks also can be globally asynchronous and locally synchronized, which minimizes those kind of delays, with the constraint being put on modern designs with the chiplet interfaces. That timing constraint are become too complicated and too wondrous with traditional techniques, said B. Levy, Vice President of the Strategic Marketing and Movers. If we have localized clocks, and typically happens across the NOC, which is part of the most traditional architectures anyway. As an asynchronous approach is a little more work, but the freedom that it gives compared to traditional clock design techniques makes it worthwhile. The file can be customized to improve the performance as well. If you want to build an NVIDIA Blackwell 2 chip, I need the highest possible bandwidth and the lowest possible power, and the largest possible bandwidth per millimeter's edge and the smallest power area, as said Patrick Haley. So the chief strategy and business officer and alien, those are things that are really important to companies like NVIDIA, Broadcom, Intel, and AMD. And all of these guys are running at between 5 to 20 terabytes per second per millimeters. If you don't have that, then the two GPUs are connected to not going to act as if they are one chip. So that you're gonna miss on latency and on power and on performance. Next is data and power integrity. Mapping how data moves to and through all of these heterogeneous components is non-trivial, and it all needs to be considered very early in the design cycle. There are two fundamental approaches that said Ashley Stevens, directors of product management, marketing, and artists. It's about whether you have a full pictures of everything in top-down view and whether you look at the design bottom-up and where you do something and then connect it to something else. The top-down approach is much simpler as because you know what they are gonna talk to, and because you know as how everything is partitioned within the system. For example, you know the memory map of the complete system, you know what there's versus if you have a system whereby you intend to connect to the arbitrary chiplet, third party or whatever. Then we much more complicated for several reasons. One of them is verification, because when you take off the top-down approach, you can verify the whole things together, but if you take a bottom-up approach, if you don't have the other part of the system, then you need very well-defined interfaces, both in hardware and software. In addition to the rapid data movement, that data needs to be remained intact, so does the power to process and move that data. In chiplet, because all the die are broken up, we have a lot of different die-to-die connections, which means that the signal integrity becomes very important, said Tim Wang Li, signal integrity application scientist and high-speed digital application product manager at Keysight Technologies. Then, of course, when you have the different die, you have power that's gonna be on a different die. How are you gonna distribute the power to all these other die and all the other dies, and that's why power integrity also becomes a problem in chiplets. But also, once you have power integrity issues, you have thermal integrity issues, it adds on to itself. The view was echoed by the numerous experts at the recent Chiplet Summit. In older design styles of SoC, you knew you had a package you could start designing with, assuming you were gonna get a certain clean supply at the power pins of your design. And Raja Chaudhry, product management group directors for Fortis at Cadence, now you have multiple chiplet and you have to set up the early model for whole system for whatever package style you're using, and you have to do it the power integrity, but it also could be done by explore the works better for your systems. What kind of technology or multi-die packaging style works and which can satisfy the constraint of what you are trying to do? And that's one of the biggest changes with the chiplet. So what becomes paramount now is trying to make sure early on, are you way off and are you in the ballpark? And can you really make this system work from a power integrity perspective? Figure 2. Multi-chip segregation and optimization using different materials, source cadence. And the thermal integrity adds yet another challenge. Stress from heat can cause warpage in a substrate, and the thinner the substrate, the more susceptible it is to warpage. This is particularly problematic for organic interposers, which require special handling, but it can affect a large silicon interposer as well. The thinner the substrate, the shorter the interconnect through the substrate, which can be through the silicon, through substrate vias or microbumps. The shorter distance improves the overall performance and reduces the amount of the power that is needed to drive signals, but warpage becomes more problematic, and it can cause the misalignment in the vias, particularly with different coefficient on thermal expansion, and those in turn can negatively impact performance, power, and signal integrity. So bridges are another option, and increasing they are being mixed in the width interposer. In fact, those bridges and interposers are being carved up into smaller pieces to minimize the thermal effect that approaches at each own set of the issues. It's not just one bridge, said Synopsys Posner. You can have multiple bridges, they are still subject to same stress and strain, but the impact is less because it's a cross-section. But as the overall size of the whole packaging increases, thermal expansion is gonna to play a part. If you look at the sum of the architecture being employed in data center, you can see why a bridge fits in. These are the tightly linked compute clusters where the actual compute is scaled. There are very tight interposable based links, but the prefers go out to make in a I/O chiplet, which could be on an organic substrate, and that fits into this kind of bridges architecture with missing and matching of the very dense interconnect and a broader, lower bandwidth per millimeters connections. Trade-offs vary by application. Not all chiplets are created equal, and not chiplets behave the same way under stress or in different package configurations. We see more and more differentiated for chiplets used in different applications, said Andy Hannigan, head of efficient electronics in the Fraunhofer IIS Engineers Adaptive System Division. In industrial and automotive, chiplets must be much more robust. That means temperature cycles in mechanical robustness vibration test. This is totally different from what we see in data centers. In the early days of the chiplet, it looked like you could use the same integration technology, the same IP, and the same things for all applications. That's not the case. You need very specific package solutions and IP for different applications. That also impacts the cost of a chiplet. If we look at the automotive data, may be as little as $20 per package, said Heineck. In data centers, it could be as much as $2,000 per package. There is usually ranging depending on the different types of packages. We need different package types in different price categories. Conclusion: Chiplets provide immense design freedom and potential for a big improvement in both performance and power. In fact, there is widespread concern that there may not be sufficient power to run all the AI data centers being planned. We are on a trajectory so far as the consumption of the power to fuel all electronics, so it's in our best interest to try to diminish what the trajectory looks like, noted Mike Ello, CEO of Siemens EDA. The number of the data centers are going to be required across the world will increase, but in the footprint of the power existing data centers, can you increase the capacity 3, 4, or 5 times the capacity and recycle the resources associated with that? It's an interesting problem. It's also one that will require much more focus on real workload economics and the laws of physics, and all of which may put a damper on just how far architects can push this approach. The future of advanced chip design is certainly heterogeneous, but it's also incredibly complicated. Getting comfortable with the approach and figure out what can be automated best and how to do it will take time. There are a lot of knobs being turned, and at this point there are still a lot of questions about what works best, where, and why. Okay, today I read this article, Chip Architecture Become Much More Complex with Chiplets. Thank you for your time. See you next time.